All right, welcome back here to Computational Biomedical Engineering, or BME 2315. In today's video, we'll be talking about Taylor series and truncation error. Basically, understanding more about how error arises in biomedical computation. So, in the last video, we looked at round-off error, which is the error that arises when we do computing or math on the computer, and that happens due to the binary format in which those numbers are stored. In today's video, we'll be looking at a different type of error called truncation error. And truncation error arises instead from taking simplified mathematical approximations to more complex formulas. And an example of that is when we cut off higher order terms of a series approximation. Those simplifications are often necessary to analyze real biomedical data, but they have a consequence in introducing additional error into these approximations. And so one example of that would be in this series approximation or series formula for estimating pi. And if you could do this for an infinite number of components, you would exactly represent pi. But instead, if you do that only for a finite number of terms, a finite number of n, then you introduce error into approximating pi. So the learning goals for this section are to understand the differences between truncation error and round-off error, and to look at how we use Taylor series to estimate mathematical functions, and finally to look at how those approximations generate error and how that propagates through the procedures that we'll do. So in Taylor series, it can exactly represent a function as long as you use an infinite series of these polynomials. So start this by making a graph of a kind of arbitrary type function, and say it has a value f of a at this point. Then we can say for x near a, then f of x equals f of a plus the first derivative of f evaluated at a times 1 factorial times, x minus a plus the second derivative divided by 2 factorial x minus a squared, and more terms like that. And so if we were to write it in a more compact form, we'd say that in an infinite series, f to the nth derivative evaluated at a divided by n factorial times x minus a n. And so if we could do this at an infinite number of times, then we can exactly represent our function. But instead, if we use a finite number, then there are likely to be errors involved in that process. So now let's look at what happens if we don't use an infinite number. Instead, we use a finite number. So if I redraw my function here, we could take a zero order approximation would simply be taking the very first term, so f of a, and there's going to be some sort of error associated with that. And so a zero order approximation might look like this, or a first order approximation would be taking the same zero order term f of a plus the next term f prime of a x minus a, and we have some additional error from the additional terms that are missing that will cause a remainder R1. So this is where n is less than or equal to 1. Or we're going to have a second, so a first order approximation would then be linear with some slope. Or we can make a second order approximation where n is less than or equal to 2. And so that will involve the above terms I'm sorry. So f of x is approximated by f of a plus f prime times x minus a plus f double prime a over 2 times x minus a squared. And so then it would have a remainder 2. So, and then a second order approximation is going to change the color real quick. So you can see this. A second order approximation is going to be a little bit better at approximating the overall function, but it's going to be a quadratic shape and not identically follow the curve. So let's see, I've got a little animation here that shows this a little bit better than my own hand sketches, that if you have this overall curved line, and then at n equals 0, n equals 1, it gets better and better the more terms that you take. And so the more terms, or the higher the n, the lower the truncation error at predicting the overall shape of our function. So that's one aspect of the Taylor series. And so now we're going to look at how we can use the Taylor series approximations to predict future values of a function. So what we're going to do is we're going to make a change of notation. And we're going to make a few variable changes. So where we had a before, we'll have xi, that's the current value of x. Where we had x, we're going to have as the next value of x. And we're going to define a step size, which is the difference between the next and the current value of x. So when we do that, we can say that we predict that the next value of our function f can be given by the current value plus f prime, that's our derivative at the current location, multiplied by a step size h, plus the second derivative divided by 2 times h squared. And you could do that to higher values, and then there'd be some remainder at the end. So one of the useful results in the math of Taylor series, that we won't go into all the details, but we'll just look at the main result, which is that the remainder is going to be can be derived to be on the order of h to the n plus 1 as h goes to 0. And so let me explain a couple things. First off, let's see what this big O notation stands for. So this O stands for on the order of. So that means it's just an approximation, just a kind of a rough version of what that number might be. And so, for example, if we say that order of 2h is about the order, is on the order of h, because it's on the same kind of multiple of this variable. Or we might say that on the order of h cubed over 4 is about on the order of h cubed. So it's saying just roughly about. And so what this is above saying is that the error, Rn, this truncation error, is on the order of h to the n plus 1. So there are two ways to decrease this error. One is to take smaller steps. So the smaller the h is, the smaller the error. And the other is to make n higher and higher, which means to take more and more terms, and so that will also decrease our error. So we can either increase the number of terms that you see up here, take higher order terms, or we can decrease our step size. Okay, so let's now, as an example, look at this fourth order polynomial and use what we've learned so far to make different approximations of that. And so as a reminder of our Taylor series formula, I put this at the top of how to predict the next values of f. So first off, also remind you that the step size, which is the difference between one location on x and the next, is given by the difference here. And we're going to say we're going to use, we're starting at 0. So we're starting at x equals 0. And we're trying to approximate or guess at where x will be, or f will be at the next iteration. So if we know that we're going to look at a difference of 1, so that means our step size is going to be 1. And so then a 0 order approximation is just going to involve the first term. So just going to involve f of xi equals 0. Okay, and so if you plug in xi equals 0 into here, that this term, and these terms will go to 0, but we're just left with a 1.2. And so that means that our 0 order approximation is 1.2. And so then the true error involved in this, so true error is the difference between the true value, which is 0.2. Sorry, I didn't set that before, but this is at 0.2. And our approximated values. So our true error is 0.2 minus 1.2 equals -1. Okay, so that's a first order approximation. Let's look at where what happens with a first order approximation. So in a first order approximation, that is f of 0 plus f prime of f0 times our step size right here, okay? And so f0 we had already solved is 1.2. And then f prime is 0. We'd look at the first derivative of this fourth order polynomial, and you see when you evaluate that at x, then the only term left is negative 0.25. Okay, and then multiplied by our step size is 1, so we get 0.95. Okay, and so to calculate our true error is the difference between our approximation and the true value, which is 1.2. Oh, I'm sorry, our true value is 0.2. And that gives us negative 0.75. And then finally, let's do a second order approximation. Our second order approximation is going to be given by f of 0 plus f prime of 0h plus f double prime of 0 over 2 times h squared. Okay, and so if we now fill in values for that, we know that this was already 1.2. We knew that this from the previous one was negative 0.25 times 1. And so now when we evaluate the second order derivative of f of x with respect to when x is 0, the only term that's going to be non-zero is this one coming from the third term. And so that's going to be given as 2 times negative 0.5 times 1 squared as a step size, divided by 2, which is 0.45. Okay, and so the true error, if we subtract the actual value I'm sorry, I put this in the wrong order previously. This is positive, this is negative. And so our true error is 0.2 minus 0.45 was negative 0.25. So what we can see is that originally with a zero order approximation, our error was negative 1. Then a first order approximation, it went to negative 3/4. And now our with a second order approximation, our guess is at negative 0.25. And so let me just kind of show that to you visually. So on our first one, that was a zero order. Then our first order approximation was that it was at 0.95. Is a little bit better, and our second order approximation was even better. So they're getting closer to the true answer as we take more terms. So to summarize this section, we found that truncation errors arise from approximating mathematical procedures, that a Taylor series can be written to predict future values of a function, and that has a zero order term, first order term, second order term, and then higher order terms. And if we take a finite number of these, then we're left with a truncation error that we know is going to be incorporated into the solution. That truncation error is on the order, or that means about, the size of h, our step size, raised to the n+1. And so there are two ways of decreasing our truncation errors. First, we can take higher order approximations, right? And so that means to take higher n, or we can take decreasing step size, which means kind of a smaller h. And either of those would be effective at decreasing our truncation error. So thanks. Hope that was helpful for you, and I'll see you next time.